Welcome to episode 11, Skydiver. What's involved? We have a fit young person weighing 60 kilograms. He or she is breathing oxygen and jumps out of a balloon at 30,000 feet under the influence of gravity and insanity and hopefully nothing else. We will model the jump to the point where the parachute is opened, 2,000 feet or 610 meters above sea level. We start with 0 vertical velocity and quickly gain falling speed up to around 80 meters per second in the upper atmosphere. Eventually we will get enough support from denser air in the lower atmosphere to slow to around 55 meters per second for parachute opening. We will keep gravitational force on any mass near the Earth as a constant. Air resistance has to come in part from air density. Air density over our atmospheric range can be looked up on the net. We place this data in a lookup table. We will call the air density up at 30,000 feet 0.3 times what it is at sea level. The model ends when we pop the chute at 2,000 feet where the air density is around 9/10 of what it is at sea level. Air resistance has to include the square of velocity, so we capture the extra work being done trying to push bits of air out of the way, while surrounding bits of air are pushing back. Air resistance has to include a value for the shape and size of the falling object that faces the oncoming wind. We ignore temperature and other factors about the air for our work here. How do we derive a shape and size factor on our own, since we are simplifying the textbook formula? We know the newtons of lift from air we need in order to obey the terminal velocity at low altitude. It has to be the same as the gravitational force on the jumper, which is 9.8 times 60 kilograms or 588 newtons. So 588 newtons has to equal our shape and size factor times 55 squared times 0.9. We divide through by 0.9 and 3025, leaving x on the right-hand side. X, our shape and size fudge factor, is equal to 0.215 in this simplified model. Let's go through the model layout. In the upper left corner, we produce our skydiver's gravitational attractive force by multiplying 60 kilograms times 9.8, getting 588 newtons. In the middle of the screen is our familiar chain for making displacement out of velocity and velocity out of acceleration. Displacement starts at 9,144 meters high, roughly 30,000 feet. Velocity starts at 0. The first step in making up air resistance is to get air density from altitude. Here is the lookup table that does this. Second step in making up air resistance is to square our velocity. We do that here. Now we need to get our shape and size factor into the mix. Here it is. We finalize air resistance force here. We sum our air resistance force, with a negative sign, and our jumper's gravitational force, with a positive sign, to get net force. Net force divided by our diver's mass of 60 kilograms makes up acceleration. We are ready to run. Page 1. Top graph is the constant force on the skydiver expressed here as positive newtons, around 588. The middle graph is falling velocity starting at 0 and getting to around 80 meters per second at high altitude, before slowing as the jumper experiences the denser air of lower altitude. The bottom graph shows the more or less linear loss of altitude over most of the 2 minutes of the jump. Page 2. Top graph is the force, the acceleration, felt by the jumper. It begins with a couple of seconds of almost weightlessness, little force, but then builds quickly to near a gravitational field of 1 g as the first terminal velocity is reached. The slowing from 80 to 55 meters per second over our model run requires that some time be spent over 1 g, or over 9.8 meters per second squared of feel. Middle graph. This shows the building of the newtons of force from air resistance. As expected, it reaches around minus 588 newtons at the first terminal velocity and stays close to that the rest of the way down. Lower graph is from our air density lookup table. At the beginning of the jump, 9,144 meters, we are at 0.3 density. The closer to the ground we get, the closer to an air density of 1 we see. The next model is soccer ball, a two-dimensional model of flight. We will treat the vertical and horizontal parts of the flight separately. That means two independent acceleration, velocity and displacement chains. Both dimensions will experience air resistance, but only one dimension, the vertical, will experience gravity. See you soon for soccer ball. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.